Thank you very much, everyone, for being here today. And we're going to talk about how you can build your own IoT assistant and what components you will need to be able to do this. So first of all, every time. So first of all, I'm an Android developer in an agency, in a tech creative agency. It's called Pixplicity. And I am also the lead for the Women Tech Makers in the Netherlands and the GDG in the Netherlands. And I also saw that there is a booth here for the local GDG. So if you're not already a part of it, and if you want to join, please go to them for more information. And recently, I also became a Google developer expert on the Google Assistant. And I travel a lot for conferences like this. If you have troubles seeing the screen, or if you want to just follow along with in your own mobile or the laptop, this is the link for the slides over here, so you can just follow along. So the three components that we're going to talk about is, first of all, the hardware, which is going to be the Android Things platform. Then we have the hardware detection. And finally, we have the NLU, which is the natural language understanding process. So that was the idea, but things happen, platforms die. So we are going to talk about hardware in general, and we're not going to see the Android things in particular. And before moving forward on how everything works, let me tell you first, like, why this talk? Why do you need to build your own IoT assistant? The whole idea started on a project, and the project was, well, an IoT device that has absolutely no touch screen or like keyboard or any kind of screen. So it's just one black box, and it had to work with voice. It has to be activated with voice, and it has to be working offline as well. And I also have a demo on my device. I am pretty sure that it's not going to work in a conference setting, but if you want to try it later on, I'm going to be here, and you can just come next to me and try it yourself. So this is like the hardware that I am trying to show you how you can build your own. And if I say like yes, yes, yeah, well, you can see those bars moving. If I say stop, it will just close. It's used, like whenever you will say something, it has specific labels, and then it can understand those specific labels. But wait, I'm here for the Android Things project and for the hardware. So where is it? Well, let me tell you a fairy tale that actually went bad. Once upon a time, a year ago, Google decided to say hello to Android Things 1.0, and then, according to them, today we are announcing support for system on modules. These modules are certified for production use with guaranteed long-term support for 3 years, making it easier to bring prototypes to markets. And everyone started to work really hard to be ready for production when those boards would come. And as the months were passing by, we started to look for those boards. Like, okay, so where are they? It seemed that they were stuck for too long at the coming soon status. And then one beautiful morning, we woke up and we read the news. And the news in February of this year, support for production system and modules will not be made available through the public developer platform at this point. System images for these boards, which means like the test boards, will remain available where developers can create new builds for non-commercial use. So, as of course things go, no matter how much we cried for help and for not killing the project, of course they killed it anyway. And if you don't know it, in Google time, 3 years means 9 months. And if I can say for myself and my company and everyone who actually put it effort and time to develop for the Android things, a platform that was supposed to be production ready, then it was a free fall. And it's still kind of free fall. We're trying to find more hardware to work on, and especially the OS. But there is nothing comparison with the Android things, especially since I'm coming as an Android developer. Anyway, that was the fairy tale that went bad. And the Android things is still a great product, is still a great platform. But of course, you can only use it for prototyping and not for production. So this is done. Let's go to the flow and how actually an IoT device is working. So first of all, you have your hardware. And your hardware cannot, of course, always listening. It has to have on the device some machine learning. And that machine learning is actually going to have the hardware detection. So the hardware is running our model, our machine learning model. And whenever the hardware detection is there, then it sends back a listener to the device and it says like, hey, hardware detected. And once we have the hardware, then the device will start listen, and we will take that audio, we speech to text, we will convert it to text, we will then run it through an NLU process, which is a natural language understanding process, and then when that is done, we will send back the result to the device. The device will query on-prem some APIs. It will provide the answer, it will speak it back with a text-to-speech. And this is pretty much the process. You can still see that the hardware is actually the main component. Like everything depends on the device and not on side services. So let's go to the hardware detection. And before diving more into the hardware detection and how the model works, I want to tell you like what does a neural network actually does. So a neural network looks pretty much like this. We have the inputs, which is the X. We multiply it with some weights, which is a W. And then we add some biases, and then we get the output. How we do that? Well, we chose TensorFlow. TensorFlow is an open source platform, and it's very, very active. It has an active community, and it makes your life much easier because of all the APIs that they have. So what we're going to cover is some of the basics for the machine learning, how neural networks work, for instance, the preparation, what you will need to do for cleaning your data, the TensorFlow model as it is by itself and what you will have to manipulate, and finally the convolution neural networks that is for audio and image detection. As a developer, for me, jumping to all these, it was overwhelming. If you just type machine learning, you're going to have some thousands of results. And when you have one problem, you really don't know what the correct approach is. So we spent months and months of research before we were actually able to build something. And this is all of our findings that I'm going to show you over here. So first of all, we are going to start with the basics. What are tensors? Tensors are nothing more than actually arrays. And the tensors can have names depending on of the dimensions of the arrays. So the scalar, for instance, is a 0D array, which can be just a number. The vector is a 1D array, which is going to be like an array of numbers. And this is how it goes. One thing that is very important is the tensor rank and the tensor shape. And the tensor shape is used to characterize the size of it. And we're going to see more examples over here. So the rank is actually the number of the dimensions. If you have an image, or like over here, then the rank will be 3, because an image has a depth, has a height, and has a width. But if you want to have the shape of it, it's going to be a more detailed version of the components that it has. So instead of just height, width, and depth, which is a rank 3, then we're going to have this tensor over there, which is 600.400.3. So the rank is 3, and the shape is the array over there. How could you actually, this is a hack that I found online and I really loved it, to actually detect very easy what the ranks and the shapes are. So the shape is the number of the open brackets. So if you count them, it's 3. So the rank of that thing is 3. And then for the shape, you know that you have a format of XYZ because it's a rank 3. So the X is going to be the number of commas that are after the first brace, plus 1. So it's going to be 0 plus 1, it's 1. Then for the Z, you have the columns, which you can count them there, it's 5. And then for the X, is Y, sorry, it's the number of rows, so it's 4. So the number, the shape of that will be 1.4.5. Yeah, shall I move on? Okay. So before you actually begin to do things with your TensorFlow model, or to be honest, to have any TensorFlow model, you need to know some basic operations for the tensors. And those that we needed for the beginnings were 3. One was the broadcasting, where if you have 2 arrays, the smallest array will become this, you can manipulate it to enlarge it and have the same dimensions that the biggest array has. Then you have the multiplication, which has the linear algebra rules. It's nothing new there. And then you have the reshaping, which is really cool. Like if you have a tensor that has that shape, like 8.2, then you can actually, with the reshape, make it a 2.2.4, which is going to have, it's going to be easier maybe to multiply it with another tensor that you already have. So there are 2 model types. The one is the regression, and the other one is the classification. The regression has an output of a number. The classification on the other side has an output of a category. So when you have a hardware detection, it kind of makes sense that you are going to have the classification model, because we want to detect the exact label of what we have for the audio. And those labels are actually called features for TensorFlow. And the features are just measurable properties of that. So if you have an image, for instance, it can be the number of wheels. This is a feature. Like a car has 4 wheels, a bike has 2 wheels. So this is a feature that you can actually put to your machine model if you have an image. If you have the audio, as we have for the hardware detection, then you have like the string labels of it. So if you want to say yes, then it's literally the string version of it. And then we have 3 types of data. The first is the categorical, the other one is the numerical, and the other one is the bucketized. So to import the data, thankfully, there is a really cool API. It's called the tf.data API, and it has 2 methods in there. The one is the tf.data dataset, and the other one is the tf.data iterator. And it enables you to build really complex input pipelines from very simple, reusable pieces. And one of the most important parts of building any kind of machine learning model is cleaning your data. I'm sure you all heard the phrase garbage in, garbage out. Whatever you put in, that you're going to get out. So there are too many things that you can actually do to clean your data and to make sure that you have a clean data set. And I'm quite positive that it's the only thing that we yet can't do without a human input. Like, you can categorize everything that you want, you can put labels in there without any human input, but you cannot clean your data without any human input. And we have this, we need to scale the feature values. We convert all the floating points from their natural range into a standard range. And this is going to help us not to run out of memory exceptions because of the floating point just going nuts. And it also helps with the model learning the appropriate weights for each feature. One of the other things that we have to do is how to handle the extreme outliers. And that is clipping. It means that whatever doesn't fit your range, if you have a range of your data being 1 to 50, and there is one data set that it has 150, that's an outlier. That you cannot put it in your data set, in your training or test data set. And then we have the binding, which will get nonlinearities by grouping it into beans. That means that if you have the geographic inputs, for instance, you will make it, you will bucketize it in like street names instead of just having the street names plus the number of the building, plus the postal code, plus everything. And finally, we have scrubbing, which is omitting values, making sure that there are no duplicate inputs in there, bad labels, and all of this. And for the hardware detection, what we did is that we literally heard probably hundreds of those samples that we randomly collected because our data set was like thousands of results. So we randomly got a few of them to actually hear them. And we also put everything into a process that it would take the waveform and you could actually see the waveform. So we would compare all the waveforms with each other and see if something seemed like a silent or something like this, then we would scrub it off. So far, so good? Okay. So then we have our labels, our features. And there are two things that you can do with them. It's just either you're going to push them to your model as they are. If there are numbers, for instance, that's fine. The number of wheels, it's 2. You don't really have to do something with that. But if it's a string feature, that changes. Then you can either have the one-hot encoding or the multi-hot encoding handle. And it looks like this. So for each string that you have, you put a 1 or 0. And the 1 is the position of that string, and all the rest is 0. And you can see here that for Rome, the first one is 1, and all the rest is 0. For Paris, the second one is 1, and all the rest are 0. So this is how you do the one-hot encoding. And one of the questions that I had in while I was doing the talk is like, why do you have Paris and France in there? Isn't it the same? Well, no, because if I say Paris, I want my machine model to actually trigger, while if I say France, I don't. It depends on what you want to do. And after learning all those, and after having a clean data set to start with, then we actually could build our model. And there are 2 parameters that you can manipulate in order to have, like, to train how you are going to train your model. The first one is the batch size, which is the number of examples that it's going to do in each step. And the steps is the total number of training iterations. So you can have like 10,000 steps of 100,000 samples in each. And then you have the periods, which is just how often you are actually going to log the output in order to be able to see how your model is faring. And why do we care that much about those parameters? Well, because of that problem, and this is a massive problem in machine learning. So the middle one is how an appropriate machine learning is. But then if you have too many steps, or if the batch sizes are too small, or stuff like this, you can either have an underfitting, which actually means that it's too generalized, and it can fare as much as a random can do. It's not really machine learning. Or it can overfit, which means that it's just memorizing everything and it's not predicting. So there are a lot of ways to do the overfitting prevention. And the one that we chose for our model was the regularization. And there are two types of regularization. The first one is the L1 and the L2 that it says over there. But what it is, it's actually penalizing the weights that you put in your model. So if you remember this, so it's just penalizing those in order to be able to predict better. Of course, if the L is too high, then you risk to be underfit. If it's too low, it's an underfit. If it's too high, it can overfit, which means that it won't be able to generalize. So you really have to find like the perfect ratio over there to be able to have a nice model. So we mentioned that there are two types of models. The one was the regression model, and the other one was the classification model. And though we said that we don't really care about the regression models because they just have a number as an output, this is how we are going to start. You're going to see in a minute why. So instead of predicting exactly zeros and ones, we use the sigmoid function and we map to predictions. So instead of 0 and 1, we can say like it's 0.5 or 0.7. So let's say that you have a value of 2. Then you can just say that, okay, it's so about 0.9. The prediction is this one. So it maps the linear values to probabilities. And why we care about that is because classification is actually using regression as the foundation of it. And the probabilities, you can see here how we can actually see how our model is faring. We have a confusion matrix. And the confusion matrix has the true positives, the false negatives, and the true negatives. Let's say that we want to have a machine learning model that it's going to predict how many spam emails we have, like if it's a spam email or not. The true positives is the number of spam emails that were correctly identified as spam emails. The false positives, let's go to the false negatives first. The false negatives is the amount of non-spam emails that were categorized as non-spam. The false positives is the amount of spam emails that were categorized as non-spam emails, and the true negatives is the non-spam that were categorized as spam. And we have 3 measurements to see how our model is going to fare. The first is the accuracy. It's pretty self-explanatory. So we can see here that we have the true positives is 1, the false positives is also 1, the false negative is 8, and the true negative is 90. So the accuracy for this model is 91%. Which you would say like, wow, that's pretty good model. But then you continue with the rest of the measurements and you say that the precision is only 50% and the recall is 11%. So the precision is when it predicts the feature, it's 50% correct. So half of the times it's correct, half of the times it's not correct. And then the recall, it correctly identifies 11% of all examples. So if we go back to our spam email example, the percent of emails flagged as a spam that were correctly classified is the precision, and the recall is the percentage of the actual spam emails that were classified correct. So you can see that the 11% of classification there, of recall there, it's a really, really bad model, although the accuracy is all the way up to 91%. And this is another way to remember the false negatives and the false positives. So the false negatives would be The false positives would be to tell to a grandma that they are pregnant, and the false negatives is to tell to a pregnant woman almost at her month that you're not pregnant. So to teach an algorithm how to recognize objects in an image or how to correctly classify audio, we use a more specific type of a neural network, which is called a convolution neural network. And the name stems from one of the biggest parts of it, which is the convolution. Convolution neural networks have a very different architecture because they were actually inspired from how our brains work. So this is a regular neural network, and you can see here that the inputs go to some hidden layers, and the hidden layers have the output, produce the output. But you can see here all the arrows, and all the inputs go to all the hidden layers, and all the hidden layers connect to both the previous level and the next level. So it's fully connected for all the layers. The convolution neural network, on the other hand, is much more different. First of all, their layers are, you can see that they are organized in 3 dimensions. It's the width, it's the height, and it's the depth. And furthermore, the neurons in one layer are not all connected to the next layer. You can see that we just get a small bit, and that bit we're actually moving forward to the next levels. And lastly, for the final output, when it's going to be produced, it's going to have a single vector with probability scored, organized with a depth dimension. So let's first see how the convolution layer actually works. What we actually do is that we have a layer and we apply that filter layer on top of our pixel. So you can see here in the math that we are going to multiply the 3 with a corresponding, which is -1, and then we're going to add all those multiplications, and then we end up with just one number. And we're going to do that as many times as we need. We will then have an activation function, which is that ReLU. And then the next layer, which is also very important, is the pooling. And what the pooling is do is, sorry. Yeah, maybe? Okay. So what the pooling is do is that it will take the biggest numbers for that layer that we are in, and it's going to pass to the next layer only those. And you can see here that this can continue as many times as we think that we need. For the hardware detection, we found out that we had to do that only twice. But if you have like maybe bigger data or like more details, then you want to have more convolution plus the pooling layers over there. And that was the feature learning. So last but not least, I hope that you're still following me. It's the natural language understanding. So everything that you needed to know for having your own machine learning model for the hardware detection, now you do. You don't have to do much research. Just look at the slides and you will know exactly what features to pick. The most difficult thing, I think, to do is to make sure that it's not underfitting and it's not overfitting, which is a big problem. What you can do to prevent this, or at least one part of prevention, is that when you create a model, you have a training set and a test set. So you train it with a training set, you test it with your testing. If the training set has an accuracy or like fails at 91%, and then you go to the testing and it's like, oh, it's 5% or 10%, then this is a big red flag for you, and you know that this is not how it should be. So the training and the matrix for the training and the testing sets, it should be pretty much the same. So let's go to the natural language understanding. And to build an IoT device, we have two options for the natural language using the Google's platform's tools. And one is the actions on Google, and the other one is the DialogFlow. But before we dive into which one actually we choose, what is the actions on Google and what is the DialogFlow? Well, first of all, what is the Google Assistant? The Google Assistant is a bot that will reply to you every time that you will say, OK, Google. And the actions on Google is the platform that you can build actions for the Google Assistant to extend its functionality. So if you want to have an action and voice action for the Google Assistant for your own company, then how do you build it? You go with the actions on Google. And the DialogFlow is where you go to build all the logic on how it should do and what it should recognize and all this stuff. So the actions on Google, you build it. At the DialogFlow, you actually have the logic part over there. So this is how the actions on Google platform looks like. And we want an IoT device. So we are going to select in this menu for the home control. And then we're going to add an action. And we see here that is, have you ever used the DialogFlow actions on Google? No, OK. So you can see here that it's actually requesting a fulfillment URL. And if you go to the documentation, you're going to see this one, which is an API. And it's this that you have to implement to actually make the Google action for the smart homes. So if you build like lights, let's say that you're building lights, smart lights, then this is where it will go and it will say like, OK, switch my lights on, switch my lights off. This is how you do it. So the second option is by using the DialogFlow and then implement this on our client side, which is, of course, the hardware. And let's see an example. Like, I want walking directions to MobiusConf. The I want and the directions to is the intent, is what the user actually wants to do. The walking and the MobiusConf is the entities, or as you say, the parameters. So the user wants directions, but you have to know how they're getting there and where they're getting at. So I'll switch. I'll switch here, and you can see here that we have a lot of intents, which is how you see what the user wants to do. And here I only have the device volume ones. And I did not type all those. There is a pre-built actions over here. And you can see that they have for cars, they have for coffee shops, they have for devices. So you can just import intents and entities that are already existing. So if I see the intents over here, let's go to volume down. You see that this is the intent, and everything that is marked is actually the entity, the parameters. And you can see those parameters over here. And there are three types of parameters. The first one is the sys number, which is just some system entities for addresses, for numbers, for locations, and stuff like this. And then you have those ones that are not knowns from the platform, and you actually make them. And last but not least, you have the users ones that you are not going to see. But then you go to the entities, and there you have all the entities. So if I click to the lights, for instance, then you see that, OK, decorations, oven, bottom, table light, like this is the lights that you're actually going to build, and you have to understand for which light the user is talking about. And last but not least, we have this fulfillment logic. And the fulfillment logic you can see that is pretty much everything that you need to do in order to fulfill that user intent. So let's say that I want directions, walking directions to go to the Mobius conf. That means that over here, I already know the intent. I already know the entities. And then I will go here, I will go the Maps API, and then the Maps API will come back to me with a response like, okay, to go to the Mobius conference, take a left, and then take a right, and then you're there. But this is where I make all my API calls and where I actually return them. We also have the one-click integrations. So if you want to build something, not just for the Google Assistant, but also for like web or the Facebook Messenger, you can actually just enable this one. And then that's pretty much all that you had to do. So for the IoT device, we used just the DialogFlow, and we didn't use the home graph API for our device. That was the best fit for our case. So to rewind, I'm not going to do that. I know that it was a lot to take in. Machine learning is not easy. And for me as an Android developer, although my studies were on robotics engineering, it was not an easy task. It took me and my team a lot of hours for research, and mostly because it's just overwhelming and you don't really know where to start. So what I really hoped with this talk is that at least now you know where to start from, and you know all the important beats as the developers that you need to get started with something. It can be an image recognition, it can be audio recognition, it can be whatever. But at least I hope that you now have the basics to at least start and do something on yourselves. And I know that it's time to party, and it's almost at the end of the day, but if you have any questions, I'll be happy to take them.
Any questions?
Hi, thanks. Sorry I'm late, but I want to ask you about how much time I have to spend to start using these technologies without any mathematical background and high skills in this field. Thank you.
So for all of the research, it took us probably about a month for 2 people just to get started with something. For the final tuning, like to be able to go to production with that, it took us way longer. I think that we're now at least half a year in and we're still fine-tuning it. You need a lot of data to get started, which I think that it's the most difficult part. It's very difficult to gather data, so that also takes a lot of time. And cleaning the data also takes a lot of time. So no matter how your skills are, just those 2 steps can take a tremendous amount of time to actually implement. For just finding around your way with how to get started, I think that like in a month you should be able to have something on your own.
The next one.
Hi, Eliza, thank you for your talk. Do you have any links to, I don't know, books or materials that would use some simple language to get you started with all those machine learning technology?
So we didn't use any books because we were really pressured by time, and books can be very helpful, but also very lengthy, and we didn't have that time. What we did was Google has some samples for TensorFlow, and there are a lot of people from the community, from the TensorFlow community, that have their own samples and their own GitLabs on how to do something. Right now, I don't really have any links, but if you want them, I can just come back to you.
Okay, thanks.
There was also one question over here, I think.
Some questions more?
Do you have any suggestion, or because you talk about features and classification, but for example, if I want to create a recommendation system, do you know, like, I don't know, any information you can give me, like what kind of model, what kind of things I have to know to start working with something like that?
Well, your features are going to be the recommendation labels, what you want to see, and your data is either going to be audio or string text, depending on where you want to have those recommendations. And yeah, it's just going to have, you're going to have, let's say, I want to go to a restaurant, and then the recommendation will be a restaurant label. And then like have a lot of those samples and matching them with a corresponding feature/label.
Maybe some more questions? So, okay, one more time, thank you for you, Eliza.
Thank you very much.